right, let's talk about 7.3 and 7.4 slope fields. And before we do this example, I want to remind us of a couple things we already know. dy dx is the derivative, which represents the slope of the tangent line. Slope of tangent. And if we think about it, if I know dy dx is 0, that means the slope of the tangent line is 0. What would it look like to have a slope of 0? Well, that's a horizontal line. If, let's say, dy dx is greater than 0, that means the derivative is positive. The slope of the tangent line is positive. Or if dy dx is negative, is less than 0, that means our slope would be falling. And last but not least, if dy dx is undefined, what would that look like? Well, there's a couple different options, but the main one I want to point out is that a vertical line would be an undefined slope. A slope field is looking at different slopes of points in a field of values. So let's look at an example. It says, consider the following differential equation. dy dx is equal to negative x over 2y. As we learned in the last example, or the last video, a differential equation relates the derivative to x's and y's. All right, so we've got a differential equation. A says to sketch a slope field of the differential equation on the coordinate plane below. What they're asking us to do is to draw a bunch of little slopes at each of these points here. Sketch a slope field means to draw mini slopes at each point. So one way you could do this is to just set up a big table. So we could create a table x, y, dy, dx. So for example, this point right here is the point 1, 1. If x is 1 and y is 1, what is dy dx? Well, in our example, dy dx is negative x over 2 times y, or negative 1/2. This means at this red point right here, the slope of the tangent line is negative 1/2. So I am going to sketch in a tiny little line to represent that slope. I know I need to make it negative, and I need to make it negative 1/2. So I'm going to draw it kind of like that. And we could go about doing all of these points by making a table, going through every single point. So 1, 0. 1, 0 would be like this point right here. And we plug in dy dx is equal to negative 1 over 2 times 0. What do we notice? This point is undefined. So I'm going to draw a tiny little slope that is undefined here. And while this is absolutely an okay way to do this, it will probably take more time than we actually want to use in something like this. So let's think through this and be a little bit more smart about how we are going to find all these slopes. Well, what did we just notice in this last problem? In this last one we did, when y was 0, this derivative, the slope of the tangent line, was undefined. So we can generalize this. If our y value is 0, dy dx, in this case, will be undefined. That means I'm able to identify that all of these slopes on the x-axis are going to be vertical lines. Notice I skipped over 0, 0, because really you'd have 0 divided by 0, which is not even undefined. It's not really anything. So I'm not going to put any sort of slope at 0, 0. Well, what else can we think through? What about if x were equal to 0? If x was 0, then I would have 0 divided by some number. 0 divided by a number is 0. So any place that x is equal to 0, my derivative is going to be 0. I have these points right here as horizontal slopes. This is helpful. This is great. We still have a bunch of other points to think through. And here's where, again, you can do kind of whatever comes best for you. I would suggest maybe a hybrid of the table and thinking it through. What do I mean by that? Well, if I start by maybe just picking a point that we haven't done yet. For example, let's say I want to find dy dx at the point, let's go with 1, 2. Let's go with this point right here. That would be negative 1 over 2 times 2, which is 4, negative 1/4. So I'm going to add in that slope. Negative 1/4 is shallower than this negative 1/2, so I'm going to try and make it a little shallower. I don't know if that was really very good, but a little bit. But now let's think about this. If 1, 2 gave us a slope of negative 1/4, what about the point 1, negative 2? How is that going to be? Well, that's because of this negative up here. If I have a negative in the denominator, it's going to be positive 1/4. So I didn't even really have to find all of the information to know that this slope right here is going to be a very shallow positive 1/4. And I can use that same logic with this guy down here. If this point at, I don't know if my cursor is doing that. If this point at 1, 1 has a slope of 1/2, then I can be pretty confident that the point at 1, negative 1 is going to have a slope of positive 1/2. So you can also think through these slopes using what we know about our xy coordinate plane, right? Positive x's, positive y's. If you would like to pause the video right now to fill in the rest of your slope field, please do so. Otherwise, I'm simply going to continue and plot a few more. So what about the slope at the point 2, 2 we'll go with? Negative 2 over 2 times 2, which is 4, negative 1/2. So this slope would be the same as 1, 1, which means I'm going to have a negative down here. And actually, we could probably be even smart enough and think through these points over here. So at negative 1, negative 1, it's going to be the same as at 1, 1, because the negative divided by a negative is a positive. So these slopes over in quadrant 3 are going to be the same as their partner slopes in the other quadrant. So if I go to, let's say, up here, slopes at 1, negative 1, and 2, negative 2 are going to be the same as negative 1, positive 1, and negative 2, positive 2. And last but not least, we've got a few more to get in there. So what about negative 1, 2? Uh-oh. Sorry about that. Give me one moment. Sorry, my computer kind of froze for a second. We were just plotting a couple more points. For example, what about the point 2, 1? Uh-oh. dy dx at the point 2, 1 would be negative 2 over 2 would be a negative 1. At 2, 1, it's a negative 1. That means at 2, negative 1, it's going to be a negative 1. That means at negative 2, positive 1, it's going to be a positive, and down here, negative. And then I didn't notice, but this and this are going to be the same, and this and this are going to be really similar. So creating a slope field, while it looks kind of complicated, is all about either noticing patterns, which you all can do, or really just doing a bunch of algebra. I would urge you to start noticing patterns like we did with finding all of our undefined slopes or all of our slopes that were 0. But at the end of the day, if you end up making a table for all those points, that is not wrong. It just would take a lot of time. So for A, we have sketched our slope field. B then says, sketch a possible solution to the curve to the differential equation that passes through the point 0, 1 on the coordinate plane above. They are asking us to plot that point, and then follow the slopes to sketch a possible solution. So let's start by plotting the point 0, 1. 0, 1 would be right here. At 0, 1, the slope is 0. And then we kind of follow along these slopes right here. Notice if I move, let's say, to the left, I start having a positive, well, I guess it depends how you want to talk about it. If we move to the left, I see it's curving down, and then we have a slope of 0, and it curves back up. And I have a possible solution based on these slopes. You're following the slope as you go. One thing to note about drawing in these curves is you must get a curve from, you must draw the entire curve. So if I had simply drawn something like this, that's really not enough. Follow the slopes until you can't anymore. Let's look at two other examples of slope fields. Notice in example 3, we are given a slope field. We do not have to calculate the slope field. It says, shown to the right is a slope field for which the following differential equations. Now, one way you could answer this question would be by going through each of these differential equations and drawing out a slope field. I would highly suggest not doing that. That is going to take way too much time. So let's think this through. Let's look at this slope field and see what we notice. The first thing that I notice, maybe most kind of obviously, is this line right here of all of these horizontal slopes. Specifically, those are slopes, dy dx, is equal to 0 here. And where is that? Well, it kind of looks about when x is equal to y. When our x value is the same as our y value, right? At 0, 0, at 1, 1, at 2, 2, etc. So let's see if that can help us, at the very least, cancel out any of these. If x and y are the same, the derivative will be 0. Well, x plus y, if they're the same, that's not 0. Sorry, again, I had to pause. Someone stopped in the classroom. Okay, what were we talking about? When we figured out that when x was equal to y, when x and y are the same, the derivative is 0. So if I have two numbers that are the same and I add them together, I'm not going to get 0. So I can tell it's not a. And this is a possibility, x minus y, if they're the same, they would be 0, okay? So b is a possibility. Negative x plus y, also, if they're the same, that would be equal to 0, again, a possibility. And this, not really going to work unless x were 1 and only 1. But for example, if I did 2 squared minus 2, if I check the point 2, 2, 2 squared is 4, 4 minus 2 is 2, that's not equal to 0, and we know the slope has to be 0 when x and y are the same. So I can cancel out a and d just by looking at this part of our graph. Then there's a lot of other things we can observe. Depending on like who you are and what you notice, you might see something a little bit different. But let's notice what else. In quadrant 2, let's focus here. In quadrant 2, I'm seeing really steep positive slopes. Steep positive. So that means when I am, let's look at these two options. Would it make sense if I have x minus y, and x is a negative, negative x minus y? So we could pick a point. Let's go 2, 4. Let's test out the point 2, 4. I shouldn't have written this. Sorry about that. Let's test out the point negative 2, positive 4. Negative 2 minus 4 would give me negative 6. Well, negative 6 would be a negative slope. So I don't think it's B, but let's check with C to make sure it would make sense. With the point negative 2, 4. Negative, negative 2 plus 4, that would be positive 6, which makes sense with this slope right here. Our answer is C. You could choose a point in any quadrant. You did not need to choose quadrant 2, but that helped us get our solution here. For example 4, match the slope field with their differential equations. So again, there's a lot of ways you can think these through. Noticing things about the slopes is important. For example, in B, right off the bat, I notice when x is equal to 0, dy dx is also 0. When x is 0, the slope of my tangent line is 0. So if I look at these right here, do any of those work? If x is 0, my derivative is 0. Well, look, if x is 0, My derivative is 0. That works here. If x is 0 for 9, we don't really know anything about x in the differential equation for 9. For 8, 0 minus y would give us a negative y, so there could be an option here, but not necessarily everyone. For sine of 0, sine of 0 is indeed 0. So 10 is also, or 7 is also a possibility for B here. But we might notice then, where is the other place where the derivative is 0 at 0? So C also has the same characteristic as B, where when x is 0, the slope of the tangent line is 0. Look at the difference in these graphs. It might also be helpful to maybe sketch in a possible solution here. If I'm following the slopes, what do I see? If I'm following these slopes, what do I see? Well, I notice that C looks like a sinusoid, right? Sine and cosine. And B looks like x squared. Well, that would make sense. If the derivative of my function is x, then that means the antiderivative of it would be x squared. So I can match B is option 10, C is option 7. Now we got to look at A and D. And again, there's lots of different ways you can go about this. I might notice, hey, this right here, when y is equal to some number, I can't really tell, they don't give us a scale, then dy dx is equal to 0. So of these two possibilities, which would make sense? Every time that y is this number, the derivative is 0, which means I'm thinking option 9 goes with A. Where y is 2 here, the slope would be 0. Let's check to see if that makes sense then for D to be this guy here. We notice again we have our slopes of 0, dy dx is 0 when we're looking at this this diagonal line when x is equal to y, which kind of checks out for our differential equation there. So we have matched 9, 7, 10, and 8. All right. The last thing I want to note, I'm a little bit worried about the audio right now, but hopefully you can hear me, is the homework. So you are given 2 documents, one about slope fields and one about verifying solutions. 7.2 verifying solutions, you can do all of these problems. Some are a little bit different than the ones we took in the notes, but I believe in all of you and you can do them. For the slope fields worksheet, so there are 4 find slope fields. You are welcome to do all 4. I only did, in the answer key, numbers 1 and 4. Why? Well, because it's kind of repetitive to do this many. And I would also say you don't necessarily need to fill in the entire chart, you just need to draw all the slopes and practice. It is likely that you will see to draw a slope field on the AP exam, but you won't be doing multiple of them, so I don't feel it's totally necessary to do hundreds of them. The other thing to note though on this worksheet is the problems 7, 8, and 9 we have not learned yet. So don't do 7, 8, and 9. Hold off on those 3 until you get back from Vocare. Have a great day whenever you're watching this.